A crystal the size of a grain of rice, 4 gold wires soldered to its corners, on a cold finger in a cryostat. It is a copper-oxide. Lanthanum, strontium, copper, oxygen in flat planes. Somebody is plotting its resistance against temperature. The trace has 2 features. At not quite 40 Kelvin, the resistance falls off a cliff to nothing, and that is the part photographed with a magnet above it. Above the cliff, there is a line running from the transition through room temperature towards red heat. It is straight, not roughly, straight to the width of the trace, across 800 Kelvin, bending nowhere. And I have spent this course being told the cliff is the interesting feature. It is not, is it?
It is not. And that is exactly where we broke off. One spin screened is a solved problem, and a spin on every site is not. What is left when every method fails is a resistivity rising straight in proportion to temperature down to the lowest temperature anybody can reach, and a metal with no identifiable, low-energy excitations at all. 4 decades of it and no agreed answer. That is your line. The cliff underneath it is the distraction. Not because a ceramic superconducting at all is uninteresting, but because nobody can explain the material it comes out of.
So the unsolved problem is the metal above the transition, and not the superconductor below it. That inverts everything I assumed walking in. I thought the puzzle was why the pairing is so strong in these compounds, and you are telling me the puzzle is the ordinary-looking state you have to cool through to reach it?
The metal above. A debt falls due first. When we did superconductivity, I named 4 things BCS cannot do in a copper oxide and said the mechanism question would arrive at the end of this course. It has arrived, and one of the 4 has changed status. The gap really does change sign as you go round the Fermi surface, established by phase, not argued from shape. Dale van Harlingen's group, 1993, built a loop contacting 2 perpendicular faces of a crystal, and the interference came out shifted by half a period. Chang Tsui and John Kirtley, the year after, photographed a spontaneous half-flux quantum where 3 crystals fused at deliberate angles meet, which a sign-changing gap must produce and a gap of 1 sign cannot.
So the shape of the pairing is no longer an inference, which does not retire that objection, it hardens it, because a phonon pulls the same way everywhere and now has to answer for a gap that does not. Name the other 3, because I remember 2 being about numbers that do not add up, and 1 being about the starting point.
All 4 stand, and that one is simply no longer arguable. The transition temperatures are far above what the measured phonon frequencies and couplings can deliver. The isotope effect is small or absent where the transition temperature peaks. And the third is today because it is not about pairing at all. Cooper's argument begins by destabilizing a Fermi C, and no cuprate parent is one. It is an insulator with no business being an insulator, and everything difficult in this subject grows out of that.
Put the ordinary metal back on the table first, because I want to be precise about what is being contradicted here. Early on, you told me the resistivity of a clean metal rises as temperature squared at low temperature. I have been carrying that as a fact about metals. Was it a fit to data, or was it derived from something?
Derived, and that distinction is the whole of today. Temperature squared is not an exponent somebody read off a graph. It is a consequence. An excitation sitting an energy of order the temperature above the Fermi surface wants to scatter. Its partner must come from a shell below the surface no thicker than the energy on offer, because both must finish above the surface where the empty states are. That is Pauli, and it is one squeeze. Then the outgoing pair must land in empty states, and once you place the first, conservation fixes the second. A second squeeze of the same thinness. 2 squeezes, each proportional to temperature, so the rate goes as temperature squared.
Not one of those steps mentions how hard the electrons push on each other. The whole thing is a count of available seats and a rule about who may sit where.
Not one of them contains the interaction strength, which is what makes it a theorem rather than a model. Turn the repulsion up 1,000-fold and the exponent does not move. Only the coefficient does, and the heavy-fermion compounds obey temperature squared beautifully at 1,000 times the free electron mass. The argument needs three things: excitations that live long enough to be called particles, a momentum for each of them sitting on a surface, and Pauli exclusion emptying the states below it.
So a metal with a resistivity linear in temperature is not a metal with a different coefficient, or a metal with a second mechanism added on top. It is a metal in which one of those three ingredients is false, and I cannot fix it by adjusting anything because there is nothing in the argument to adjust.
One of the three is false. The measurements say which one, though not why, and we will get there. What is measured has two terms. One carries no temperature dependence, electrons bouncing off impurities, reporting the purity of your sample, and nothing about the physics. The other is what the electrons do because of each other, and in a normal metal, it climbs as the square. In an optimally doped cuprate, it is a straight line, a residual plus a constant times the temperature, first power. That constant is the entire content of the anomaly.
How far down in temperature does the straight line actually survive? Because the superconductor gets in the way. Below the transition, there is no resistance to measure, so for all I know, the line curves over into a quadratic under the dome, and the whole story evaporates.
That objection held the field up for 20 years, and the answer was to remove the superconductivity with a field big enough to kill it. In a 2009 paper LED by Rob Cooper, with Nigel Hussey and others, lanthanum strontium copper oxide was taken to the strongest fields available, the superconductivity stripped off, and the resistivity was still linear down to a few Kelvin. Louis Taillefer's group and others repeated it a decade later across several cuprate families. The line goes down as far as anyone has looked. It does not curve over.
And upward it runs to 1,000 Kelvin without saturating, which you showed me before. So the same law holds over 3 orders of magnitude in temperature, and inside that range sit the magnetic exchange, the phonon spectrum, the pseudogap scale, half a dozen energies I could name. None of them puts a kink in the line.
None of them leaves a mark, and that is close to the strangest thing about it. Any ordinary transport mechanism has a characteristic energy, and when the temperature crosses that energy, the curve changes shape. That is how you identify a mechanism. Find the feature, read the scale off it. This curve is featureless. It behaves as though the material has no characteristic energy for the electrons to notice.
That sounds like the beginning of an argument rather than a complaint. If the material genuinely has no characteristic energy for the electrons, that is a strong statement. And strong statements usually have consequences I can guess before you derive them. Can I guess this one?
You can, and you should, because it is the cleanest guess in the subject. Scattering is described by a rate, 1 over a time. To make a rate, you need an energy, because Planck's constant converts one into the other. So the question is, what energy sets the rate at which an electron here loses its memory? Name the candidates you have.
The Fermi energy, which in a metal is electron volts, tens of thousands of Kelvin. The Debye energy, the top of the phonon spectrum, a few hundred Kelvin. The magnetic exchange between neighboring coppers. The repulsion between 2 electrons on one site, and last and smallest, the temperature itself.
Now put Landau's answer into that language. A Fermi liquid scattering rate is the thermal energy squared divided by the Fermi energy divided by Planck's constant. 2 powers of temperature upstairs, 1 large energy downstairs. So the rate is small. The excitation lives far longer than its own oscillation period and gets better at it as you cool, because the big energy in the denominator never moves while the temperature falls.
And the linear law has one power of temperature upstairs and nothing downstairs but Planck's constant. Every one of those large energies I just listed has dropped out of the answer. The metal is not consulting its own Fermi energy at all.
Not consulting it. The rate is the thermal energy over Planck's constant, times some number of order 1, and that is not a small rate. It says the excitation loses its memory in roughly the time it takes to oscillate once at its own frequency. It is not a badly behaved particle. It is not a particle.
How big is that in something I can feel? If I am sitting at 100 Kelvin, what is the lifetime, and how does it compare with anything I have met?
A thermal energy at 100 Kelvin is about 9 millielectron volts, and Planck's constant divided by that is a bit under 1/10 of a picosecond. At 10 Kelvin, under a picosecond, and the measured rates sit at that value, not near it to an order of magnitude, at it, with the coefficient landing between about 1 and 2 across materials with nothing in common. Jan Bruin and colleagues put a long list on one plot, and the overdoped cuprate work found the same slope in compounds with different chemistry and different Fermi surfaces. The name is Planckian dissipation, and it is the fastest rate anything is ever observed to have.
Observed or allowed? Those are very different claims, and you moved from the second to the first without marking the step. If there is a bound, something must forbid going faster, and I would like to know what.
You are right, and I said that badly. There is no theorem. Nothing forbids a faster rate, no derivation produces the coefficient, and there are systems sitting above the value. The phrase Planckian bound gets used loosely, and it should not be. What is true is narrower, across metals whose resistivity is linear in temperature. The slope corresponds to a scattering rate equal to the thermal energy over Planck's constant to within a factor of 2, and nobody has explained why.
All right, is there an ordinary way to get a linear resistivity? Ordinary metals do it too. Copper is linear at room temperature, and nobody calls copper strange.
There is, and it may be the right answer here. Scatter your electrons off phonons. Above the Debye temperature, the number of phonons in each mode is the thermal energy divided by the phonon energy, so the population grows in proportion to the temperature, and so does the scattering rate, and the resistivity is linear. Copper does that above about 150 Kelvin, so the cuprate may simply have a soft mode, a phonon, a spin fluctuation, and the straight line is the ordinary high-temperature behavior of scattering off it.
But that explanation is only valid above the mode's own energy. Below it, the mode freezes out. You taught me the phonon contribution dies off as a high power of temperature once you drop under the Debye scale, which is precisely why an ordinary metal's resistivity curves over at low temperature. The cuprate line does not curve over. With the field on, it runs down through 10 Kelvin and keeps going. What energy would your soft mode have to still be thermally excited down there?
Essentially 0, which kills it. If the line continues to 1 Kelvin, the boson doing the scattering must have modes soft enough to be excited at 1 Kelvin, and at 10, and at 300, with the same rate law throughout. A mode with no energy scale is not a phonon. It is a mode sitting at the point of ordering and never arriving, which is a far stranger proposal than the one I made. So the phonon account survives only in the high-temperature half of the line. Below about 100 Kelvin, it is dead, and there is no established replacement.
Then give me the outcome of all this in one sentence, and make it exact, because this is the thing I most want to be able to say afterwards. Which assumption of Fermi liquid theory does a strange metal violate?
The one the whole theory is built on, that an excitation near the Fermi surface is sharper than the energy it carries. Landau's argument works because the decay rate times Planck's constant is an energy width, and that width shrinks faster than the excitation's own energy near the surface, so the ratio goes to zero and you have a good particle. In a strange metal, that ratio is of order 1 at every temperature. The width equals the energy. No small parameter, therefore no quasi-particle. The surface itself survives. Photoemission still finds the locus where the excitations are gapless. But there is nothing sharp sitting on it for Pauli to count seats around. What dies is not the exponent, it is the object. What dies is not the exponent, it is the object.
So the small parameter was never the interaction. It was the ratio of the excitation's own width to its own energy. And Landau's whole catalogue rides on that ratio going to zero. In a strange metal it sits at 1 at every temperature, and there is nothing left that deserves to be called a particle. Take me back to the material itself then, because you said the trouble starts before any doping at all. What is the parent compound, and why on earth does it insulate?
Strip the strontium out of that crystal, and you have lanthanum copper-oxide, and the action is entirely in flat planes of copper and oxygen. Count the electrons, and the relevant copper orbital is half full. 1 electron on every copper, and the band it lives in exactly half filled. Now apply everything from the first act of this course. A half-filled band is the definition of a metal. Empty states sit immediately above occupied ones, an arbitrarily small field moves charge, and lanthanum copper oxide should conduct like aluminium.
And instead it is a dark ceramic that does not conduct at all. That is not a small discrepancy. That is band theory getting the most basic question about a material exactly backwards.
It is an insulator with a gap of about 2 electron volts, which is why it has a color rather than a shine. Neville Mott wrote down why in 1949, thinking about nickel oxide, which has the same scandal. Band theory computes what 1 electron does in the average field of all the others. It never asks what happens when 2 arrive on one site at once, with a Coulomb repulsion of several electron volts between them. Call that the on-site repulsion, and call what an electron gains by spreading over the lattice the hopping.
And when the repulsion beats the hopping, moving stops being worth doing. Let me say the mechanics of that back to you, because I want to be sure it is not just a slogan. On a half-filled lattice, every site already has 1 electron, so there is nowhere to hop to that is empty. Any hop at all means landing on an occupied site and paying the full repulsion in exchange for the hopping energy. And if the repulsion is 10 times the hopping, that trade is never taken.
That trade is never taken, and the electrons freeze 1 per site. Not because there is a gap in the band structure. There is not, but because the traffic is jammed. That is a Mott insulator.
How do I say the difference from a band insulator in a way that would survive an examiner leaning on it?
By counting electrons per unit cell. A band insulator has an even number per cell, so the bands fill in pairs, leaving a real gap between the last full band and the first empty one. Silicon, diamond, table salt. Turn the interactions off and it is still an insulator. A Mott insulator has an odd number per cell, so turning the interactions off must make it a metal, because half a band cannot be full. Its gap is not in the single particle spectrum at all. It is the cost of putting 1 electron onto a site that already has one, and it vanishes the moment you pretend the electrons ignore each other.
So the insulating state has 1 spin, 1/2, sitting on every copper with nowhere to go. Those spins are not free to do nothing. They must talk to each other somehow. Do they order?
They order, and the mechanism returns all day. The electrons cannot hop, but quantum mechanics lets them hop virtually, out and back, and a virtual excursion lowers the energy exactly as in second-order perturbation theory. Now ask when it is allowed. If 2 neighboring spins point the same way, the trip is forbidden outright because the destination orbital holds an electron of the same spin. If they point oppositely, it is allowed. So anti-parallel neighbors gain an energy that parallel neighbors do not.
Which is anti-ferromagnetism, arriving out of a repulsion and an exclusion principle, with no magnetic force anywhere in the argument. And the size of the gain should be second order, the hopping squared over the repulsion, because that is the energy denominator for a virtual state with 2 electrons on one site.
Hopping squared over the repulsion times 4. In the cuprates, that is around 130 millielectron volts, measured by neutron scattering and by 2 Magnan-Raman, 1500 Kelvin in temperature units, an enormous magnetic energy. So the plane is an anti-ferromagnet with a huge exchange and lanthanum copper oxide orders with alternating spins at a Néel temperature of a few hundred Kelvin, set not by the exchange but by how weakly one plane talks to the next.
There is a wrinkle I have read about and never understood. People say the gap in a cup rate is not really a copper-to-copper gap at all, which sounds like it ought to wreck the picture you just built.
It modifies it. In the real material, the oxygen levels sit between the 2 copper ones, so the cheapest excitation is moving an electron off an oxygen onto a copper, not from copper to copper. That makes it a charge transfer insulator rather than a textbook Mott insulator. Fu-Chun Zhang and Maurice Rice showed in 1988 that this changes less than it looks. A hole on the 4 oxygens around a copper binds with that copper's spin into a singlet, and the singlet moves just like a hole in a one-band repulsive model. That is why the field works on a one-band model of a 3-orbital material.
Doping, then. Strontium, in place of some of the lanthanum, pulls electrons out of the planes and leaves vacancies behind. I think I can predict this one, and I will commit before you tell me. Removing a fraction of the electrons unjams the traffic. There are empty sites now, so an electron can hop into one without ever doubly occupying anything, and it never pays the repulsion at all. So I should get a metal whose carrier density is the doping, a dilute metal like a lightly doped semiconductor. Few carriers, ordinary behavior, resistivity going as temperature squared, because once the jam is cleared, there is no reason for Landau's counting to fail.
The carrier count is right, and it is measured. The Hall number in the underdoped cuprates tracks the doping, and Sven Badu and colleagues in 2016 watched it jump from the doping to 1 plus the doping as they crossed a particular concentration. Everything else you said is wrong, and it is wrong in the way that makes this subject hard.
Where does it fail?
The hole does not move through an empty stage. It moves through an antiferromagnet, and it cannot take one step without wrecking it. Follow a hop. The hole moves left, which means an electron moved right, and that electron now sits where its neighbors expect the opposite spin. It has left a mistake behind it. Step again, and there are 2 mistakes. The hole trails a string of misaligned spins, and every link of that string costs about the exchange energy.
So the hole is not free in any sense. It is tethered to where it started by a cost that grows the further it goes, which is a confining force, and I have never met one of those in a metal. That alone should make the carriers heavy, and heavy for a magnetic reason rather than a lattice one.
Heavy for a magnetic reason, with a bandwidth set by the exchange rather than the hopping, and the spins rearranged to relieve the string, so the object that moves is a hole dressed in a local disturbance of the magnetic order. Then a second effect, sharper still. Remove a fraction of the electrons and count the spectral weight appearing at low energy. How many states are available to move into? A band picture says you have opened that same fraction. What is measured is twice that.
Twice? Where does the extra come from, if I have only taken out 1 electron per hole?
From the fact that an empty site accepts an electron of either spin, and both are available at low energy. In a filled band, you remove 1 electron and open 1 state. In a Mott insulator, you remove one and open two, and the weight comes down out of the high-energy branch at the repulsion scale. So doping does not drain a reservoir. It transfers weight from high energy to low at a rate no band structure produces.
And I take it there is no small parameter anywhere in the middle. At zero doping, I have an insulator with local moments and an enormous exchange. At heavy doping, I have an ordinary metal that obeys Landau. In between, I have two known limits and nothing to expand in.
Nothing to expand in, and that is the technical statement of why 40 years have gone by. The repulsion over the hopping is 8 or 10, so you cannot expand in the interaction. The doping is a few percent, so you might expand in that, except the state you would expand around is an insulator whose ground state on a two-dimensional lattice is not exactly known either. Every controlled method this course has taught you needs a starting point close to the answer, and here there is none.
The phase diagram then. Everybody who writes about cuprates draws the same picture, and I have looked at it 100 times without ever having it built up piece by piece. What are its axes?
Horizontal axis, holes doped into each copper-oxygen unit, from 0 out to about a third. Vertical axis, temperature, from absolute 0 to a few hundred Kelvin. At the far left, on the vertical axis itself, the antiferromagnetic insulator we just built. Dope it and the magnetic order dies fast. By about 3% it is gone, because the holes are so effective at scrambling the alignment.
3%. So a handful of holes per 100 coppers destroys an order held together by 1500 Kelvin of exchange. That is the string argument showing up as a number, and it is a violent one.
Violent, and then a superconducting dome. It starts around 5%, peaks at about 16, which everybody calls optimal doping, and returns to 0 near 27. To the right of the dome, the metal is a Fermi liquid. Resistivity is temperature squared, a proper quasi-particle peak in photoemission. A Fermi surface whose area is what counting all the electrons says. Landau's theory works there, and works well.
So the ordinary metal is on one side, the insulator is on the other, and the superconductivity sits between them. That placement cannot be an accident. It looks like the material superconducts precisely where it cannot decide what else to be.
Which is the first hint about the mechanism, and we come back to it at the end. Now the part that concerns us. Directly above the top of the dome is a wedge where the resistivity is linear, opening upward from a point on the doping axis near 19%, and that is where everything we have discussed lives. To the left of it, above the dome's left flank, is a fourth region, bounded by a line coming down from high temperature at low doping and meeting the axis around the same place.
And that fourth region is the pseudo-gap, which is the one word in this field I have heard most often and understood least.
The pseudo-gap. The part of this diagram that most needs explaining and that has attracted the most incompatible ones.
What was actually seen, not the interpretation, the measurement, and by what instrument?
Magnetic resonance in 1989 in 2 experiments. Henri Alloul's group in Orsay measured the shift of a nuclear resonance line in yttrium-barium copper oxide, which reports the magnetic susceptibility the nucleus feels from the electrons around it. In an ordinary metal, that shift is flat with temperature. In the underdoped cuprate, it starts falling 200 Kelvin above the superconducting transition. Warren and colleagues at Bell Labs saw the companion effect in the relaxation rate.
So the electron's ability to respond magnetically is being switched off well above any temperature at which something happens to the resistance. What makes that a pseudo-gap rather than simply a gap?
The absence of everything that normally comes with a gap. A real gap turns things off exponentially below a sharp transition. This turns them off smoothly, beginning at a temperature people write with a star, and there is no thermodynamic signature of a transition there. No latent heat, no jump in the specific heat. Something removes low-energy states with none of the usual accompaniments.
Then photoemission must have got involved, since that measures directly where the states are and where they are not.
Photoemission gave the picture that stuck. Mike Norman and colleagues, in 1998, went round the Fermi surface of an underdoped bismuth cuprate above the transition and found that whether there were states at the Fermi level depended on which direction you looked. Along the zone diagonal, states. Near the flat regions, none, gapped. So the Fermi surface was not a closed loop. It was a set of disconnected arcs, and they shrank as the temperature fell, collapsing onto the points where the superconducting gap has its nodes.
A Fermi surface with ends is an alarming object. Everything in this course that used a Fermi surface used the fact that it closes. Luttinger's theorem counts the electrons by the volume enclosed, and an arc encloses nothing. Does that mean the electron count is simply unavailable in that region?
It means exactly that, which puts the pseudo-gap at the center of the argument. The interpretations divide badly. One camp says, pairing without phase coherence, electrons pair at the star temperature but have no common phase until the lower one, so you get a gap with no superconductor, and a thermoelectric signal above the transition does look like moving vortices. Another camp says it is a competing order. Charge density waves were found in yttrium-barium copper-oxide by X-ray scattering in 2012, right where the pseudo-gap lives, and quantum oscillations at high field 5 years earlier had shown the Fermi surface down there is a small pocket, a couple of % of the zone, which is what happens when something of longer periodicity cuts a large surface up.
And a third possibility is that it is neither of those, and the pseudo-gap is a state of matter in its own right, with a broken symmetry nobody has yet identified.
A live position with candidate order parameters, including currents circulating inside each copper-oxygen unit that break the symmetry between clockwise and anti-clockwise without any net magnetism. Those measurements are contested. What everybody agrees on is the doping where the pseudo-gap ends and that the carrier density changes there. What nobody agrees on is what closes.
The wedge above the dome, opening upward from a point on the axis, that shape has to be a hint. It is exactly the picture of a critical point, except that the point sits at 0 temperature rather than at some temperature where a transition happens.
It is a critical point at 0 temperature, and that is the organizing idea the field reaches for. Go back to the liquid-gas critical point. There the correlation length diverges, patches of every size, no characteristic length, and the system forgets what it is made of. Now the quantum version. Instead of tuning temperature, tune pressure or field or doping at absolute 0 until the ground state itself becomes critical. There the correlation length diverges in space and the correlation time diverges too, because at 0 temperature, space and time enter quantum mechanics on the same footing.
But nobody experiments at absolute 0. What use is a point you can never stand on?
Its use is everything above it, and here it stops being a picture and becomes an argument. Sit at the doping directly above the critical point, at a small non-zero temperature. The system has no intrinsic energy scale because the scale that would have set one has been tuned to 0. So what energy is left to it?
Only the temperature. And if the temperature is the only energy in the problem, then anything with the dimensions of a time has to be Planck's constant over the thermal energy times a pure number, because there is nothing else in the room to build a time out of. That is Planckian dissipation, falling out of dimensional analysis, with no model of anything.
With no model, scale invariance produces it, and a scattering rate proportional to temperature produces a resistivity proportional to temperature, so the wedge above a quantum critical point should be exactly the strange metal, and it should open upward, because moving away from the critical doping restores an energy scale, and below that scale ordinary behavior returns.
What is the evidence that it is right rather than merely apt? Because so far you have shown me a shape agreeing with a shape, and I could get that from a coincidence.
In the heavy-fermion compounds, the case is strong, and they are the cleaner laboratory. Cerium, copper, gold, and ytterbium, rhodium, silicide are the standard ones. There you tune with a magnetic field, which is continuous and reversible, cross the critical value, and map the fan directly. Linear resistivity above it, quadratic away from it, an effective mass diverging as you approach. That is a critical point doing what one should.
In the cuprates, it is not so clean, or you would have LED with them.
In the cuprates, it is a hypothesis with problems. You have to say what is critical, and nobody knows. The candidates are the end of the pseudogap, an antiferromagnetic transition hidden under the dome, and a charge order, and they do not all sit at the same doping. Worse, in several families, the linear resistivity is not a narrow fan. It covers a broad range of doping, which one critical point does not produce.
What are the actual proposals then? 40 years is a long time, and somebody must have written something down that can be argued with.
The oldest one that still matters is deliberately not a microscopic theory. Chandra Varma and colleagues in 1989 wrote down one assumption, that the material has charge and spin excitations whose response, instead of having a characteristic energy, depends only on the ratio of frequency to temperature. Scale invariance put in by hand. From that, a scattered list of anomalies follows. The linear resistivity, a photoemission line shape as broad as its own energy. The tunneling, the specific heat. They called it a marginal Fermi liquid. Marginal because the quasi-particle is destroyed as slowly as it can be. Width and energy vanish together rather than one beating the other.
That is a description of the answer rather than a reason for it, though. It assumes precisely the scale invariance the whole puzzle is about, and then congratulates itself when scale invariant things come out.
It assumes exactly that, and its authors said so at the time. Its value is that one hypothesis accounts for a list of anomalies people had been explaining separately. Real information about how many independent mysteries there are. And there is a check most candidates fail. In 1991, Puan Ong's group at Princeton measured the Hall angle in yttrium-barium copper-oxide and found its cotangent goes as temperature squared. And 35 years later, no theory gives both unbidden, while the ordinary resistivity in the same crystal goes as the first power.
Two different powers in one measurement on one sample. That reads as two scattering rates in the same metal, which I did not think was a thing a metal could have.
That is the question, and Anderson's answer was that they belong to two different excitations. That the electron in these planes has come apart into a piece carrying charge and a piece carrying spin with different lifetimes. Which brings us to the idea that dominated the first decade. Georg Bednorz and Alex Müller at IBM Zurich announced the discovery in 1986. Anderson published his response in Science within months, reaching back to something he had written in a materials bulletin in 1973 about spins on a triangular lattice.
The resonating valence bond. Build it for me from the half-filled plane, because I have only ever met it as a phrase.
Take the half-filled plane. Instead of spins alternating up and down in a rigid pattern, pair them off. Each spin forms a singlet with one neighbor, a valence bond, exactly as two electrons pair in a chemical bond. There are enormously many ways to tile the lattice with such pairs, all of about the same energy, so the true ground state resonates over all of them. Anderson's move was to say, this liquid of singlets is the parent state, and that when you dope it, the pairs are already there. You have only to let them carry charge.
That is a genuinely beautiful idea, and it explains the placement on the phase diagram without effort. So what happened to it?
It got the sign-changing gap right before it was measured. It forced the field to take doped Mott insulators seriously, and it produced the language of spin and charge coming apart. A spin-on carrying spin and no charge. A holon carrying charge and no spin. What it has not produced is a controlled calculation anybody can check. The formalism needs a gauge field invented to enforce that no site holds two electrons, and the theory is strongly coupled. And the one place where spin and charge provably separate is a chain, an argument that is one-dimensional and does not carry to a plane.
Is there anything genuinely new? Something that is not a 1980s idea being refined for the fourth time?
One line, because it comes from outside the field. There is a family of solvable models, a random interaction model of Subir Sachdev and Jinwoo Yi, later taken up by Alexei Kitaev, and gravitational constructions where a metal is described by a charged black hole in a higher dimensional spacetime. Those produce Planckian dissipation naturally rather than by assumption, and have no quasi-particles by construction. They are not models of a copper oxide. What they establish is a point of principle. A metal with no quasi-particles dissipating at the thermal rate is a consistent thing to be.
Something slipped past me back at the parent state. Anderson's liquid of singlets at half filling has no antiferromagnetic order in it, but we measured antiferromagnetic order in lanthanum copper oxide with anneal temperature and everything. So the picture is simply wrong for that material.
For that material, yes, and Anderson knew it. His argument was that the ordered state and the resonating one are close in energy, so a small change tips it over. But the state itself is a real possibility. It has become a subject with its own name, and it is where the second act of this course comes back. A quantum spin liquid.
Define it against the wine bottle, because that is the picture I have used for order ever since the ferromagnet. The free energy develops a circular trough, the marble sits somewhere in the trough, and which point it chose is the order parameter.
Then here is a state that never chooses, spins 1/2 on a lattice, coupled antiferromagnetically, cooled as far as you can reach, and no magnetic order of any kind. No Bragg peaks, no static moment, no broken symmetry, nothing to be the marble. The obvious explanation is that it is a paramagnet, spins pointing every which way because they are hot. But it is not hot. It is hundreds of times below the exchange coupling them, so they are interacting fiercely and still refusing to order.
Why would they refuse? Something has to be stopping them, and at that temperature it cannot be thermal agitation.
Two things together. Frustration. Put antiferromagnetic spins on a triangle and no arrangement makes all three pairs happy. So instead of one ground state, there are many, and the system faces a choice it cannot settle on energy grounds. And quantum mechanics, because spin 1/2 is the most quantum spin there is, and the fluctuations between those competing arrangements are large. The lattices where this is hoped for are the triangular one and the kagome, which is triangles joined at their corners.
And it is a phase, and not merely a failure to be anything else, because no order also describes a gas, and I do not want to be sold a negative as though it were a discovery.
It is a phase, and telling it from a gas of unrelated spins is the entire experimental problem. Its identity lies in what it is made of, rather than what it looks like. The ground state is long-range entangled. You cannot build it from independent local pieces, and its properties depend on the topology of the surface you put it on, the same invariant we met in the Hall plateaus. Its excitations are fractional. Flip one spin, changing the total by 1 unit, and the disturbance comes apart into two objects, each carrying half a unit.
What does an experiment see if the state has no order parameter to point an instrument at?
A continuum where a sharp line ought to be. In an ordered magnet, neutron scattering finds magnons, a well-defined mode with an energy for each momentum, and we watched one earlier in this course. If the excitation instead splits into two fractional pieces, sharing the energy and momentum however they like, the neutron cannot make one sharp thing, and you get a broad smear. Tianheng Han and colleagues in 2012 grew large crystals of a Kagome mineral, Herbert Smithite, and found exactly that smear, with no magnetic order down to well under a Kelvin.
Is that settled? You said they found the smear, not that they found a spin liquid.
It is not settled, and Herbert Smithite is the best candidate there is. Some zinc and copper swap places as the crystal grows, leaving stray spins between the planes that contribute their own signal, exactly where the interesting one is, and whether the ground state has a gap is argued in both directions, with good measurements on each side. The other headline case is a ruthenium chloride said to realize a solvable honeycomb model of Kitayev's, where a thermal Hall measurement came out at half the quantized value, which would be a sighting of an excitation that is half a fermion. Some groups reproduce it, and others do not.
So the position is a strong theoretical case that these states exist. Several materials with the right symptoms, and no single example the field agrees on. That is the same sentence you gave me about the strange metal in a different corner of the subject.
The same sentence, and the corners are connected because the resonating liquid was proposed as the parent of the copper oxides. Nail a spin liquid down in a material, and the question of what the cuprates do at low doping looks different overnight.
All of this is chemistry, though. If I want to test an idea about strongly correlated electrons, I have to find a compound that happens to have the right numbers, grow it, and take what nature hands me. Is there any way to build the parameters instead of hunting for them?
There is now, and it is the most important experimental development in this subject since the copper oxides. Take two sheets of graphene and stack them, rotating one by a small angle. The lattices no longer line up, and where they nearly do, you get a beat pattern, as when two mesh screens overlap. That is a moire, and its period is the graphene lattice spacing divided by the angle in radians. Rotate by about 1 degree, and the pattern has a period of some 13 nanometers, 50 times the atomic spacing.
So the electrons see a new periodic potential with a period far longer than the atoms provide. A long period means a small Brillouin zone, and a small zone means the band has hardly any room to disperse across, so the bandwidth collapses.
Collapses, and at one angle astonishingly so. Alan MacDonald and Rafi Bistritzer predicted, 7 years before anybody built one, that near 1.1 degrees the band goes essentially flat. The kinetic energy nearly vanishes. Now think what that does to the ratio governing everything today. Correlation is the interaction energy over the bandwidth. You cannot easily change the Coulomb repulsion, but drive the bandwidth towards zero and the ratio goes to infinity, however weak the interaction is.
Strong correlation manufactured out of geometry rather than out of chemistry. And the knob is an angle, which is not something anyone has ever been able to turn before.
Yuan Cao and Pablo Harillo Herrero and colleagues at MIT did it in 2018 in 2 papers published back-to-back. In the first, at the magic angle with the moire band half-filled, the device was an insulator, with no gap in its band structure to make it one, which is exactly the definition we built earlier. In the second, doped slightly away from that filling, with nothing but a gate voltage, it superconducted at about 1 7/10 Kelvin.
An insulating state produced by interactions, with superconductivity on doping either side of it. That is the cuprate phase diagram, drawn in a material with no copper, no oxygen, and no magnetism to speak of.
With every energy scale 2 orders of magnitude smaller, and every knob electrical. In a cuprate, changing the doping means growing a different crystal. Here you turn a voltage and sweep the whole diagram on one device in an afternoon. And the strange metal is there too. The resistivity above the superconducting region is linear over a wide range, at a slope near the Planckian rate.
Then it is the same phenomenon, and the puzzle has moved into a material we can build. Is that the consensus?
It is not, and here is the competition. Because the bands are so flat, scattering off acoustic phonons becomes enormous and stays linear down to much lower temperatures than in a normal metal, and calculations reproduce the measurements with no exotic physics. That debate is live. So the statement is that twisted bilayer graphene has a cuprate-like phase diagram, and whether its strange metal is the same phenomenon is being tested rather than known.
Then take the other route. There is a model everybody believes contains this physics, the hopping plus repulsion model we wrote down in the second conversation of this course, which took about a minute to state. Why can nobody solve it?
In one dimension it is solved exactly. In infinite dimensions it is solved. In two, which is the case the copper-oxygen plane hands you, it is not, and the obstruction is specific. The workhorse method is Monte Carlo. Rewrite the quantum problem as a sum over weighted configurations and sample the important ones. For fermions, the weights come out negative for half the configurations, so what you want is a small difference between large cancelling numbers, and the noise grows exponentially with system size and inverse temperature. That is the sign problem, and it is believed to be hard in a precise computational sense.
What do the best classical calculations actually say then? Not what people hope the model does, what the numbers show.
Something that ought to be better known. A large collaboration, LED, by Ming-Pu Chin, published a result in 2020 for the pure model, nearest neighbor hopping plus the on-site repulsion at cuprate coupling. In that model, at the doping where superconductivity should be strongest, there is none. What wins is stripes. The holes segregate into rivers separated by antiferromagnetic regions. 4 years later, several of the same people added the next nearest neighbor hop, a diagonal hop present in real cuprates, and superconductivity appeared, coexisting with stripes on the whole doped side.
So, whether the minimal model superconducts at all depends on a term that somebody could reasonably have dropped as a small correction. That is uncomfortable, and it also makes me wonder whether minimal model was ever the right ambition.
It is uncomfortable, and it is where the subject stands. Stripes and pairing sit so close in energy that a small term decides between them, which may be a nuisance or may be the physics. A material poised between competing arrangements is exactly what produces a phase diagram shaped like the cuprates.
Then what does a quantum simulator do that a computer cannot?
It does not compute the model. It becomes the model. Cool fermionic atoms, lithium-6, potassium, to a few billionths of a degree, cross laser beams to build a standing wave egg carton, and the atoms hop between wells and repel when they share one. The lattice depth sets the hopping. A field near a scattering resonance sets the repulsion. You have not approximated the Hamiltonian, you have constructed it, and there is no sign problem, because nature is not sampling anything. Then a microscope images the lattice site by site.
What has that produced so far?
Anton Mazurenko and colleagues in Marcus Greiner's group produced an antiferromagnet across about 80 sites of a square lattice, the correlation length growing until it reached the size of the system, then doped it with holes and watched the magnetic correlations survive out to about 15%. That is the parent state of a cuprate, built from atoms, imaged one site at a time. There has been steady progress since, including a machine reported last year that runs the lattice inside a cryogenic environment to get colder still.
And the temperature is the whole question, presumably. How cold is cold enough, and how far away is that from where the experiments are?
The Mazurenko experiment ran at about a quarter of the hopping energy. The best estimates put the sign-changing superconductivity in this model at 2 or 3 hundredths of the hopping. So the gap is roughly a factor of 10 in temperature and cooling is the central engineering problem of the field. Not measurement, not system size. Cooling.
Then say precisely what a simulator would have to demonstrate to settle this. I want a criterion somebody could fail, not an aspiration.
Two things, and neither alone is enough. First, take the repulsive model on a square lattice, doped away from half-filling, cool it below that pairing scale, and measure pair correlations between sites far apart. Do they fall away to nothing, or approach a constant as the separation and the system grow? A pair correlation that survives to long distance, with the sign-changing pattern around the pair, is superconductivity in that model, and it settles whether the model contains it. Second, above that temperature, measure how charge relaxes and ask whether the same Hamiltonian gives a resistivity linear in temperature at the Planckian rate.
And if it gives you the pairing and the straight line, the model is right, and what remains is a hard mathematics problem. If it gives neither, the model is wrong and something has been left out of it. Either way, I learn something, which is not usually true of an experiment this expensive.
Both outcomes are worth the machine. If the plain model does it, the ingredients were the ones written down in 1963, and the difficulty was purely one of solving. If not, the missing ingredient is on a short list. The diagonal hop, the oxygen orbitals put in explicitly, longer-range Coulomb, phonons, and you add them one at a time and watch. Meanwhile, digital quantum computers attack the model from the other side, running the time evolution of a two-dimensional version on 70-odd superconducting qubits, and a couple of hundred neutral atoms in optical tweezers have been driven into a state whose topological signatures were then measured.
I want to separate what is established from what is argued about, because I could not have done that when we started, and I think I can now.
Separate them.
Established. The parent compound insulates because of repulsion and not because of band filling, and it is anti-ferromagnetic because virtual hopping is permitted only between anti-parallel spins. The things that condense are pairs of charge 2 electron charges from flux quantization in a cuprate ring. The gap changes sign around the Fermi surface from the loop and the tricrystal. The normal state above the dome has a resistivity linear in temperature from 1000 Kelvin down to the lowest temperature reachable once a field has stripped the superconductivity off, with no quasi-particle peak in photoemission, and a scattering rate at the thermal energy over Planck's constant. And the pseudogap exists, with the carrier density changing where it ends.
All defensible. Now the other column, and be as specific.
Not established. What binds the pairs? What the pseudogap is, pairs without phase coherence, a competing order, or a state of its own. Whether there is a quantum critical point under the dome, and if there is, what becomes critical at it? What the low-energy excitations of the strange metal are, given that they are not electrons and not any named replacement either. And whether the hopping plus repulsion model contains the answer at all, which is at least now a question with an experimental route rather than only an argument.
One correction, and it goes to your first item. What binds the pairs is asked as though the answer must be a glue, a boson exchange between two electrons, the way phonons are exchanged in BCS. That framing may be the error. In a doped Mott insulator, the pairing may not be an attraction at all, but the system's way of lowering the magnetic energy the holes are disrupting, in which case there is no exchanged particle to find. Nobody knows whether that is right either. But notice when a question has smuggled in an assumption.
4 decades and no agreed mechanism then. It does not resolve, and I am not going to be handed one at the end.
It does not resolve. No better measurement is about to close it. Thousands of people have been on it for 4 decades.
Here is what I notice at the end of 12 of these, and it is not a summary. Every time this course explained something, the explanation had the same shape. and I did not see it until we reached the case where it fails. Helium climbing a wall was explained by a single macroscopic phase, not by helium atoms. A metal was explained by a dressed excitation, not by electrons. A magnet was explained by an order parameter, a critical point by a diverging length, a Hall plateau by an integer belonging to a filled band rather than to any particle in it. In every one, somebody found the object the physics is actually about, and it was never the thing in the Hamiltonian.
Never the thing in the Hamiltonian. Go on.
So the strange metal is not unsolved because the equations are harder than the others. The Hamiltonian has been on the board since 1963, and it is 3 lines long. It is unsolved because nobody has found the object, no quasi-particle, no order parameter, no invariant, no macrostop wave function. And the search for the right variable is what all 12 of these have been, whether or not it succeeded.
That is the whole of Anderson's argument, and worth saying in his own terms, since he wrote the essay, proposed the resonating valence bond, and did not live to see it settled. He said the ability to reduce everything to simple fundamental laws does not imply the ability to start from those laws and reconstruct the universe. People read that as a remark about scale. It is sharper. It says that at each level the right variables are new, and that finding them is not a matter of working harder on the level below. Nothing shows it better than the copper oxides, where the microscopic laws have been in hand for 40 years, and it has not helped.
There is one more thing in that diagram I want you to say out loud, because it undercuts any tidy version of the story. The ordinary metal is to the right of the dome, and the insulator is to the left, and both of those are understood. The unsolved region is the one lying between 2 solved ones.
Between 2 solved ones, which tells you what kind of problem it is. Both limits are tractable because each has something small. On the right, the excitations are nearly free. On the left, the electrons are nearly stationary. The middle has neither, and it is precisely where the material does its most interesting thing. That is not a coincidence of this compound, it is the general condition. The phase is worth having live, where no expansion converges, which is why this subject keeps producing law rather than detail.
The crystal is still on the cold finger. The trace is still straight.
Still straight in every laboratory that has measured it, in materials sharing nothing but being bad metals near a magnetic insulator. And when a law that simple has turned up here before, with no explanation attached, the explanation was always a collective object nobody had thought to look for. A pair with a shared phase, an excitation dressed past recognition, a number belonging to a whole band. There is no reason this one should break the pattern. Somebody will find the object. Nobody yet knows what kind of object it is.
And until then, the plot stays on the wall.
Until then, it stays on the wall, and it is the best question in physics that anybody has ever written down in a straight line.